The next example I give is of a flow cycle that we have now talked about yesterday. And here is the cycle that we will look at. In the problem set, I have given some simple problems there. There are more practice problems we can give. So what it is we looked at yesterday is basically a Rankine cycle, and that's the same thing I have drawn. And we say that what is flowing in this is water, H2O. And the cycle consists of 4 components: a boiler, a turbine, a condenser, and a pump. And we connect these by pipes, which we will put there. The exit of the boiler to inlet of the turbine, there is this pipe. The flow is in this direction. The turbine exhausts the steam and comes into the condenser, where it flows over tubes carrying cold water and becomes saturated liquid and comes down. This flows into the inlet of the pump, which flows into the boiler. In a real power plant, some of these pipes could be like 100 meters long, 150 meters long. Some pipes could be small. For example, this pipe could be just like about 3-4 meters. And this would be even smaller than that. So that doesn't matter for us. And we are given that the turbine has inlet conditions of 200 bar and 400 degrees Celsius. It expands to 50 degrees Celsius. Then it is condensed to saturated liquid. And we want to know what is the work output of the turbine, heat input into the boiler, the cycle efficiency, what is the heat dissipation rate in the condenser, what is the power required for the pump. All these are required for selecting these equipment when we want to put the cycle together. So all these calculations have to be done. And these states tell us what is the pipe diameter and the material and the type of pipe that you are going to put for these types of conditions. So the cycle as such, what we are going to do now, is the basic first step that one does in the design of any power plant or any cogeneration system or any combined cycle power plant or any other place where such a flow system is done. It could be a refinery, a paper mill, anything. This is the first diagram that is made, and you put mass balance and energy balance on this and work out what are the parameters that you are getting in this. So we do that for this particular cycle, and the way we will do it is that we first say that there are 4 states, and we will say that this is state 1, here we have state 2, this is state 3, and here state 4. And we are assuming that in this pipe there is no change of state. So we are assuming that pipes are ideal flows, no friction, no pressure drop, no heat transfer with the surroundings. In reality, there will be a slight decrease in pressure and temperature because it may lose heat if it is above ambient temperature. For this analysis, in this course, we assume that to be constant. And then what we will do is, we will plot all of these into a table. So we make a table where in the first column we write down which is the state point that we are looking at. So we have 4 states, 1, 2, 3, and 4. And beside this, we will list all the properties for that particular state. So first we will put pressure and units as bar. Then we'll get the temperature in degrees Celsius, dryness fraction if applicable, specific volume, meter cube per kg. In a flow system, we know that internal energy is not coming into the equation. So we can say that I will only worry about specific enthalpy, kilojoules per kg, and specific entropy, kilojoules per kg per Kelvin. And now let us first write down what do we know about this system. The first is the pressure is given at state 1 as 20 bar, and the temperature is given as 400 degrees Celsius. And if we look at the property tables, we know that this becomes superheated, so dryness fraction is not applicable. So this is now we are starting to infer what we from this information. So this is not applicable. And since these two are given, we can go to the property table, get the specific volume, we can get the specific enthalpy and write it there. From the table, we can get the specific entropy and we can write it over there. So these we calculated. This is what was given to us. What more is given to us? In state 2, we are given that it is temperature is 50 degrees Celsius. And to know what is the state, we see that the flow has gone through the turbine, which means that we use the condition that an ideal turbine S2 will be equal to S1. And so this value will come here also, 7.129. This came here. With this and this, we compare it with the saturation specific entropies and find that this is in the wet state. And so we calculate from there and say that for this thing, dryness fraction comes out to be 0.871, and the pressure is the saturation pressure at 50 degrees Celsius. This is 0.12352. Again in bar. Some of these tables will give it in kilopascal. We have to convert it and then put it here. And specific enthalpy, again we look from the table, this is 2284.06. So now state 2 is known completely. The next thing is what happens at state 3. We are told that it is completely condensed and becomes saturated liquid. Cooling is a constant temperature process, constant pressure process. In this case, it is saturated state. So wet substance going in, condensing, this is a constant temperature process. It will go to saturated liquid. That means X is equal to 0. So this is saturated liquid. And now from here, we can again go back to the tables and pick up everything that we want. The pressure is known, which is the same pressure as this one, 0.12352 bar. Specific volume, 0.001012 meter cube per kg. Specific enthalpy from the tables, 209.34. Then we come to state 4. So well, this is at the outlet of the pump. We know that the outlet of the pump, the pressure has to be equal to the pressure at the inlet of the turbine because the process of heat addition is constant pressure. So that tells us that this will be equal to P1. So P4 equal to P1, and that across the pump entropy remains the same. So S4 is equal to S3. So from there we can now start putting things here that this is 20 bar. Dryness fraction not applicable. We know this is a compressed liquid state. We need to know the specific enthalpy, and for that we will use the relation in pumping. We have a liquid state only. H4 minus H3 is equal to P2 minus P1. So we will write this as P4 minus P3, and this could be either V3 or V4, doesn't matter because this specific volume doesn't change. We do this calculation. H3 is already known to us. H4 will come from here, which is 211.35. So now all the specific enthalpies are known to us, all the states are known, and we can visualize this cycle on the TS diagram. So this is state 1, which is superheated above the critical point, 400 degrees Celsius. This is state 1. The turbine process is isentropic. We have assumed that it comes down here to state 2. Then condensation is constant pressure, constant temperature. It comes to state 3. Then isentropic compression, it comes there. And then we have this whole process. This is the heat addition process. So that's our, by looking at it, we know that this is a Rankine cycle. And we now then just go back and put all the values in there. And for each equipment, we will write the equation and solve it. But we don't need to do it every time. We can say that globally, the common assumptions for every equipment in this is that there is steady state and that changes in kinetic energy are equal to 0 and changes in potential energy are equal to 0. Every equipment has one inflow and outflow, so the mass flow rates are same, and then we can calculate Q dot in the boiler. This turns out to be 151852.5 kilowatts. And the way we do that is that this is m dot H1 minus H4. Similarly, you can calculate the turbine work output. This is 48217 kilowatts. Work to the pump minus 100.5 kilowatts. And thermal efficiency, the thermodynamic efficiency, this is turbine output minus pump input divided by heat supplied to the cycle, and this turns out to be, in this case, to be 0.316 or 31.6%. And we can also do another check that we know that if it's a cycle, the second law told us that cyclic integral of heat is equal to cyclic integral of work, and you can check that by taking all these numbers that is indeed the case. Sometimes it may not be exactly the thing, one last digit could be off, but that's because of round off that has been done. So no need to worry about that part. So that's how we can solve this thing. And on the diagram itself, the way people would put this data is that we say that here we will write the state, here we will write the pressure, the temperature, the specific enthalpy, and the mass flow rate. So we write the 4 numbers here. Similarly, we can write the 4 numbers here, 4 numbers over here, and 4 numbers here. So this very important information, which is the starting point of design of such systems, contains all the information that we require to say, for instance, buying a pump. And so we say that I need so much mass flow rate, I'll give some margin on it. I need this as the inlet pressure, this as the outlet pressure. Which are the pumps that I should buy? This will tell us that this is the flow rate, these are the inlet outlet conditions, which is the boiler that one should buy. Same thing with condenser, same thing with turbine. So these are the things that are the beginning of the designing and then finally putting together of a system like this one. Real systems will have more components than this, but the process that I have just mentioned is same for all of these. Okay, so that was the examples that I have given. Now we'll continue taking questions, but before that, there's one question from an earlier lecture. Somebody asked what is the difference between the Gibbs free energy or Helmholtz energy. So let's have a few minutes on that. This is a picture that summarizes the 4 energy properties that we have learned. U is the energy needed to create a system. It is the internal energy of the molecules. H, we've learned, is this plus work needed to make room for it. The different language that is there, it's slightly different meaning. Helmholtz free energy, which we call A, U minus Ts. This is this minus Ts. This is so this is energy needed to create a system, which is U minus energy provided by the surroundings or the environment. And G, which is Gibbs free energy, this is H minus Ts, which is the total energy required to create the system, make room for it, which is H minus energy provided by the surrounding, this part. So those are the 4 types of energies that will come in thermodynamics. And it's not just in this thermodynamics that it will come in. but they will come in, say, mixtures, reacting systems everywhere. These are the four things that we will come across.